Hey there everyone. In this situation what we have two currents that are next to each other, and these currents are traveling either parallel or opposite to each other, and we need to figure out what kind of influence they have on each other. As a matter of fact, because these two currents are traveling next each other, each current creates a magnetic field that actually comes within the vicinity of the other current. If there is a current that is traveling within the vicinity of a magnetic field, then that current will feel a force, as we learned before. Okay, but before we try to solve this problem, we need to remember two things. We have two right-hand rules. Right-hand rule number one, okay? And for right-hand rule number one is that you use basically what we know for the magnetic field, your four fingers, your velocity is, or the current in this case, is this thumb, and the palm of your hand is where the force is, okay? So that's the right-hand rule. We also need to use right-hand rule number two, and that's for a wire that is carrying a current, and we need to find the direction of the magnetic field. So if this was a wire and the direction of the current is up, then you grab on the wire so that the thumb points to the direction of the current like this, all right? And then the magnetic field loops around. So if it's to the right, that this is my right, it's going this way, and if it's the left, it's going out like that. So it loops around like this, okay? So it loops around like this, all right? So that's the right-hand rule number two. Another thing we need to remember that's going to involve in solving this problem is the equation of the force of the magnetic field created on a wire, and that would be I/L/B sine theta. We also need to remember for this one the magnetic field created by a wire, a straight wire, which is mu0 I over 2 pi r. Okay, and now let's go and tackle that problem. We know a current is a traveling charge, and when a current is present in a long straight wire, it creates a magnetic field around it. Okay, let's see how that magnetic field is using the second right-hand rule. Okay, so we have the current for I1, and if we grab on it like this, so we know under the current, this one here, under the current, there is a magnetic field created. I'm going to call it B1. So B1 under I1 is inside the page, and above I1 here, it's outside the page. It's going to form like a circle, okay? Now, how would a current like I2 within the vicinity of I1, and there's a magnetic field created by I1, I'm going to call it, I called it B1, how would this current feel the force of that magnetic field? Because this current is a traveling charge within the vicinity of a magnetic field. Let's use the right-hand rule number one now to find the force of that. Okay, so we put our four fingers within the direction of the magnetic field, which is inside the page. That's our four fingers. And the current is this, okay? So the magnetic field force would be up, like that. Okay, that's good. So I'm gonna make this here like that. And I am going to call this force of 1, because it's created by the magnetic field of 1, on 2. I'm going to write it this way. So this is read as force of 1 on 2. Now I'm going to change the colors so that we can look at I2. I2, using the right-hand rule, how is I2 making a magnetic field direction within the vicinity of this? Let's use the right-hand rule number 2 now. Again, this is the current. Grab on the current so that your thumb shows where the current direction is, and it seems that above the current it's coming out. So in the vicinity here, the magnetic field created by current number 2 is this way, or this direction, within the vicinity of I1. Okay, now using the first right-hand rule, let's see how that traveling charge, which is I1, is influenced by the presence of magnetic field number 2 here. Okay, so I'm gonna use the right hand rule. So the magnetic field is coming out, okay, and the current is going up, so like this. Okay, so this is the current and the magnetic field is coming out of the page, so the magnetic field force is gonna come down like that. So I'm gonna put that here, and that's what F2 on 1, and that's how the magnetic field created by current 2, which is B2, is going to influence current 1. So that's why F2 on 1 here. So it seems that when the two currents are traveling parallel to each other within the same direction, there will be a force on each wire that is going to bring them both closer to each other, just like we see here. Okay, so let's find the value of this force. So I'm going to use the value of this force. The value of this force, F1 on 2, let's just take F1 on 2, and that will be, the object of interest is I2 times L2 times the magnetic field created by B1 times sine theta. Again, theta, because this is going inside the direction of the page and the current is going like this way, so inside the page, and the current is perpendicular, so that's always going to be 90 degrees, and sine 90 is equal to 1. Okay, now we need to find B1, the value of B1 here at this point coming from I1, and that will be using the equation that we learned, the magnetic field created by a straight wire, which is mu naught times the current I1 divided by 2 pi the distance, which is here given by R. Okay, so plug this one here, and the end result will be F1 on 2 is equal to I2 comes down, L2 comes down, B1 is mu naught I1 divided by 2 pi R. There is no sine theta, so I'm going to rearrange this equation. F1 on 2 is equal to I1 I2 L2 times mu naught over 2 pi R, and that's it. If we want to find the opposite now, F2 on 1, it's gonna follow the same kind of like algebra here, but we can actually do it quickly. F2 on 1 is going to be equal to, I'm going to put the same thing, I1 and I2 are in the same equation. Now instead of L2, I'm just going to put L1. Okay, mu naught over 2 pi R. So it's the same thing, but F2 on 1, so the influenced or the interest, the object of interest is I1, that's why you have to put L1 here. F1 on 2, the object of interest is 2, and that's why you have to put L2 here. Okay, we can make it even easier. We can find something easier, and I'm going to write this in green. The force, the mutual force between two wires per unit length. So you don't have to worry about the length at all. It's just going to be equal to I1 I2 mu 0 over 2 pi R. So that would be much easier to remember if you want. Okay, so to recap quickly, if there's two wires next to each other, they're both carrying a current, each one carrying a different current, I1 and I2. They influence each other by a force caused by a current running within the vicinity of a magnetic field. So basically, this one here, this current here, creates a magnetic field that has this direction within the vicinity of this current. Using the first right-hand rule, we find out that the force of this current on this current is going to be up. Now, the same scenario can be followed because this wire is carrying a current. It creates a magnetic field whose direction is outside the page within the current I1. Okay. Now what happens is that using the first right-hand rule again. This is the traveling direction for my thumb. This is my four fingers, and we find out the direction of the force of this current on this current going this way. All right. Now, using a couple of equations, F1 on 2 is equal I2L2, B1 sine theta is equal to 1, and plugging in B1 because we are trying to find the force of 1 on 2. So 1 is created by B1 on 2, which is on L2. And plugging these numbers together, we get this general equation. Okay? So if you want to find the force of 1 on 2, it's the same equation, the same terms, but 1 on 2, you put L2. F2 on 1, you put in L1. All right? Or you can find finally the force per unit length, and you don't have to worry about the length of either of them. It's the same equation for both, since it's a mutual force. Okay? The unit of the force on the length is, of course, the force is in Newton, the length is in meters, so it's Newton per meter. Okay? Now what happens if the two currents are going opposite in the direction? If the two currents are going opposite in direction, using the right-hand rules, again, but the first one and the second one, you will find out that the force is going to be repulsive. So F1 on 2 will be like that, and F2 on 1 will be like that. So they're going to repel each other. So just memorize it if you want to. If the two currents are going parallel to each other, then the force between them will be attraction. If the currents are going opposite to each other, like this one, then the force will be repulsive. And that's it. Thank you very much.